This is the video solution for CE 570, problem 51. The problem is stated that we have a square piece that has a unit thickness of 1 and a hole with a radius of 1 in the center. The deformation map is shown. Required for this problem are to compute the volume of the hole in the undeformed and deformed configurations, the perimeter area of the square in the undeformed and deformed configurations, and the perimeter area of the hole in the undeformed and deformed configurations. So, starting with the volume of the hole in the undeformed configuration, we simply have the area of the circle multiplied by the thickness. So with a radius of 1, the volume becomes pi. In the deformed configuration, to take the volume, we have to integrate the volume of the determinant of the deformation gradient. So the deformation gradient is shown. We took the determinant of that and solved it to be 3 beta times z1 plus beta times z2 plus 1. So since we're dealing with a circular object, we're going to convert everything into polar coordinates. z1 is going to become 2 plus r cosine theta, and z2 will become 2 plus r sine theta. We added 2 to each of these terms because the center of the circle is at 2, 2 in the undeformed condition. So taking the integral over the volume as shown is with respect to r, theta, and z3. So the volume becomes pi times the sum of 8 beta plus 1. For part B, we're looking for the perimeter area of the square in the deformed and undeformed configurations. For the undeformed configuration, we simply have 4 sides that are each 4 units long and have a thickness of 1. So the perimeter area would be 16 square units. In the deformed configuration, to find the area, we have to integrate the determinant of f times the magnitude of the inverse transpose of f acting on a vector m, where m is perpendicular to the area that we're investigating. So let's start with the area of the surface that's perpendicular to E1 in the undeformed condition. M would simply be 1, 0, 0, and Z1 is 4 in the undeformed condition. So shown is the inverse transpose of the F tensor. We also have calculated the determinant of F and shown the calculation for F times the inverse transpose of F. So after they act on M, you have a vector that's 12 beta plus 1, negative 4 beta, and 0. Taking the magnitude of that vector, we get the formula that we need to plug in to our integral for the area. So once we integrate that over the area, which means with respect to z2 and z3, we then have our equation for the final area of that side in the deformed condition, which is the square root of 1 plus 24 beta plus 160 beta squared. The calculations for the area of the surface perpendicular to E2 in the undeformed condition are very similar. The only differences being that M is now 0, 1, 0, and Z2 is 4. So shown are the calculations, again, for the inverse transpose of F and the multiplication of F and the inverse transpose. We once again acted on M, with M this time being 0, 1, 0, and take the magnitude of that vector. We plug in that magnitude into our area integral once again to find the area of the side perpendicular to E2 to be the square root of 1 plus 8 beta plus 160 beta squared. For the areas of the surface that are perpendicular to E2 and E1 in the negative direction, those surfaces didn't deform. So their areas are the same as they were in the undeformed condition, which are 4 and 4. So we sum all these terms up to get the total area of the figure.
Okay, so for part C, we're going to look at the perimeter area of the hole. So for the undeformed configuration, simply just the circumference of the hole times the unit thickness, resulting in an area of 2 pi. For the deformed configuration, we use the same formula for the area as before. Or for m, we use cosine theta, sine theta, and 0 since we're dealing with a circular object. We take the determinant of f, as shown, and we take the inverse transpose of f, shown here, multiply the two, resulting in this matrix, and multiply that matrix by the vector m. And since we are dealing with a circular object, we'll convert z1 and z2 into polar coordinates using the same rationale as earlier. We take the magnitude of this, and we get square root of w squared plus square root of w squared plus v squared, where w and v are defined here. Plug it into our area formula, we get the following. And this concludes our video solution for problem 51.